Say you're running a chat app with 50,000 banned words on file. Every single message has to get checked against all of them before it ever shows up on someone's screen. And it has to happen in milliseconds because you've got millions of messages a day coming in. Slow the check down and users start complaining about lag. Cut corners on it and something awful slips through live. That's the exact problem we're building a fix for. By the end of this, you'll have a real API sitting behind a real page. You paste in a message, hit scan, and it tells you safe or flagged, plus which banned phrases it found and exactly where. Every piece of that, the matching engine included. We are hand building, not importing. Think about who this sits behind. A trust and safety team owns the word list and keeps adding to it. Every message that gets posted routes through this API before anyone else sees it, and it has to answer fast whether that list has 500 words or 500,000. The user never notices any of this. They just get a chat that works. Say you just loop through your 50,000 banned words. For each one you check if it appears in the message. That's 50,000 scans for every single message. At 1 million messages a day, that's billions of checks. The naive loop isn't slow because string search is slow. It's slow because you're asking the same question 50,000 separate times per message. The question we actually need answered is different. Can I check for all 50,000 words at once in a single read of the text? Think of a spell checker that's already memorized every word in the dictionary. It reads your sentence once and flags every misspelling as it goes. It doesn't reread your sentence 50,000 times, once per dictionary word. That's the same trick an algorithm called Aho-Corasick plays with our band. Word list. Build one structure out of all the patterns ahead of time. Then read each incoming message exactly once, left to right, and it flags every match it passes along the way. No rereading the same text thousands of times. Let's build this piece by piece instead of dumping the whole diagram on you. It starts with a person typing a message into a page in their browser. Nothing fancier than that yet. That message doesn't check itself. The browser sends it over as a post request to a backend we're about to write. One endpoint. Moderate. We're picking FastAPI here for a boring reason. It lets one Python process serve both the moderate endpoint and the page itself. So there's no second server and nothing to wire together across origins. It also validates the incoming JSON for us instead of us hand checking it. The backend itself doesn't know how to spot banned words. It just hands the text off to the automaton we're about to build. And that's where the actual matching happens. Take all your banned words, cat, car, cart. Instead of storing them separately, merge them into a tree. Shared prefixes like ka become a single shared path. Every branch point marks where a word could end. This is the whole trie, a node with a dict of children and a list of patterns that end there, plus an insert that walks the tree character by character, creating nodes when it needs to. Every banned word we insert shares whatever prefix it already has in the tree. Now scan a real message character by character. You are matching CAR when the next letter breaks it. A naive scanner would go back to the very start. Aho-Corasick jumps sideways to the closest still valid match instead. This is the exact same trick as KMP's failure function, just generalized. Instead of one array pointing backward through a single pattern, you get a failure link at every trie node pointing to the longest suffix that's a prefix of some other pattern in the set. That's why building it needs a BFS over the whole trie instead of a single linear pass. So the text itself is still only ever read once, left to right. This is the part that turns a plain trie into an automaton. We walk it breadth first, and for every node we find the longest suffix of its path that's also a valid prefix somewhere else in the tree. That's its failure link. When a match breaks mid-word, we jump there instead of starting over. This is the payoff of the last two stages. One loop over the text, one character at a time. On a mismatch, we follow the failure link instead of going back to position 0, and whenever we land on a node with outputs, we yield every pattern that just matched. The automaton gets built once when the server starts, not on every request. Then Moderate just runs our own search function over whatever text comes in and hands back a flag boolean plus the exact matches. Send in a real message through the API. The scanner walks it once left to right. It flags scam link at position 12. and a banned slur at position 40, same single pass. No matter how many thousand words are in the list, the naive loop's cost went up every time you added a word to the block list. This one doesn't. Once the automaton's built, the search only cares how long the message is, plus however many matches it finds. That's the O of n plus z you'll see this called. We didn't want to just assert this scales better, so we wrapped both versions in a plain timing loop. Time bar buffer counter before and after the scan, same message, same machine, block list grown from 10 words up to 10,000. The naive loop's time climbs right along with the list. The automaton barely moves because it only cares about the message length, not how many words you banned. That's the whole thing. The try, the failure links, the single pass search, and the endpoint that ties them together all in one file. Run it with UbiCon main app and it serves the API and the page off the same port. On the other end is just a plain page, a text area, a button, and a fetch call to moderate. It reads back whatever the API sends and shows safety or flagged with the matched words. Nothing exotic because it doesn't need to be. Talk is cheap. Here's the actual page being used for real in a real browser. Nothing staged. Go back to that 50,000 word chat app from the start. Every message still gets checked against the whole list. It's just that now the check is one pass over the text instead of 50,000 separate scans. Each piece we built has one job. The try holds the words, the failure links keep the scan from ever restarting, and the search function and endpoint turn that into something a real app can call. That's a real moderation engine built from nothing but a try, some failure links, and one pass over the text. Debugging is hard. Hitting follow is not.